All right, let's get into it. Today we're tackling two concepts that are just, well, absolutely essential in mechanical design. First, we've got torsion. That's the twisting force you see in everything from drive shafts to the bolts holding your car together. And then we have stress concentration, which is like this hidden enemy that can cause a perfectly good part to just snap when you least expect it. Honestly, if you can get a handle on these two things, you're well on your way to designing parts that are strong, reliable, and just plain work.
So, here's our game plan. We're going to start in a perfect world looking at pure torsion in a simple circular bar. Then we'll see what happens when things get a little more real, with different shapes. After that, we'll go hunting for those nasty stress spikes, learn some clever ways to design around them, and finally, we'll put all the pieces together to see the big picture.
Okay, first things first, the ideal case. Before we can understand the complex stuff, we have to build a solid foundation, and that means starting with the absolute simplest scenario you can imagine, a perfectly uniform, perfectly circular bar with a pure twisting force applied to it.
So, what exactly is torsion? The best way to think about it is like wringing out a wet towel. That twisting action, that creates a state of stress inside the fibers of the towel. In engineering speak, it's the stress you get when you apply a twisting moment, or what we call torque, to a shaft. Simple as that.
Now, for our ideal case math to work out nicely, we have to set some ground rules. Think of these as our lab conditions. We're assuming the bar is perfectly straight and has a uniform circular shape. The material has to be the same everywhere and in all directions. And critically, we're only twisting it, no bending or pulling, and we're not twisting it so hard that it gets permanently bent out of shape. These assumptions are what let us use the really clean, simple formulas. And here they are, the two workhorse formulas for simple torsion. That first one for the angle of twist, you'd read it as theta equals T times L divided by J times G. This tells you exactly how many degrees or radians the bar is actually going to twist. The second one gives you the maximum shear stress, which is tau max equals T times R divided by J. This one is so important because it tells you where failure is most likely to begin, right on the very outer surface of the shaft.
And what's beautiful about that first formula is just how intuitive it feels. If you make the shaft longer or apply more torque, of course it's going to twist more. That just makes sense. And on the other side of the equation, a stiffer material, that's G, or a thicker, more robust cross-section, that's J, is going to fight against that twist. So yeah, longer and skinnier means more twist, stiffer and beefier means less.
Okay, so that was the nice, neat world of perfect circles. But let's be real, parts aren't always round. They're often square or have keyways or all sorts of other shapes. And as soon as we leave the comfort of the circle, things get weird. And here is the absolute key takeaway. When you twist a circular shaft, a flat cross-section remains perfectly flat. But with a non-circular shaft, that same flat face actually warps. It bulges in and out of the plane. It's a crazy thing to visualize, but it means all our simple assumptions just go right out the window. The stress distribution is no longer a simple straight line, and the math, well, it gets a whole lot hairier. This leads us to a fundamental rule of thumb in design. If you have a certain amount of material to make a shaft, a circular cross-section is always going to be the stiffest and strongest against torsion. And to help understand why, there's this really cool trick called the membrane analogy. I want you to just imagine stretching a soap bubble over an opening that has the same shape as your part's cross-section.
This soap bubble analogy it's just brilliant. The more air the bubble can hold, the stiffer the shaft is in torsion, and a circle, of course, holds the most volume for a given perimeter. But even better, the steepness of the bubble at any point tells you exactly what the shear stress is there. So you can instantly see that the stress is highest where the bubble is steepest, in the thick parts, and it's practically zero right at the very tip of a sharp corner.
Okay, so we've looked at the big overall shape of a part. Now we need to zoom in way in to the tiny little details, because this is where a silent killer for any design lurks, and it's called stress concentration.
And this really gets to a core question every designer has to ask. I mean, think about it. When something breaks, where does it break? It almost never just snaps in a clean, smooth section, no. It fails right at a hole, or a sharp corner, or where the part suddenly gets thinner. Why does it always happen there?
Well, the answer has a name, the stress concentration factor, or KT. It's actually a pretty simple ratio. You take the true maximum stress right at that little feature, and you divide it by the average, or nominal stress, you'd calculate for the whole section.
What it is really is a multiplier. It tells you exactly how much that little geometric feature is amplifying the stress right in that one tiny spot.
Let's make this real. This table shows data from what's called a photoelastic model. It's a cool technique where you use special plastic and polarized light to literally see stress patterns. Now, the average stress across the part with the hole is about 480 psi, but look at the stress they measured right at the edge of the hole. It's a jaw-dropping 1130 psi.
So let's do the math. We take that maximum stress, 1130, and divide it by the average stress, 480. And what do we get? We get our stress concentration factor, KT. For this particular setup, it's 2.35.
And what that number means is absolutely crucial. That little hole isn't just a minor issue. It creates a massive stress spike. The stress right there at the edge is more than double what the rest of the part is feeling. This becomes the weak link in the chain, the place where a tiny crack is almost guaranteed to form and grow.
Right, so we've identified the problem. We know the enemy. Now, how do we actually fight back? Let's talk about these smart, practical design choices we can make to tame these dangerous stress spikes.
And this brings us to one of the most fascinating and frankly counterintuitive ideas in all of mechanical engineering. Sometimes, to make a component stronger, you have to strategically remove material. I know it sounds completely backward, but it's absolutely true. Here's the best way to get your head around it. Stop thinking of stress as just a static force. Instead, visualize it as something that flows through the material, like water flowing in a river. A sharp corner or a hole, that's like a giant, jagged rock dropped right in the middle of the current. It doesn't stop the water, it just creates a ton of violent turbulence right next to it. Our job as designers is to smooth out that riverbed, to carve a gentler path so the stress can flow smoothly around the obstacle.
And here are some very real practical ways we do that every day. Instead of a sharp 90-degree corner, you always use the biggest fillet radius you can get away with. If you have a shaft that steps down in size, you can add a small relief groove to ease that transition. You can even drill smaller relieving holes on either side of a main hole to help coax the stress flow away from it. It's all about smoothing the path.
Okay, let's zoom back out for the finale. It's time to bring all three of these ideas together: the basic twisting of torsion, the warping of non-circular shapes, and the danger of stress concentration.
Because here's the bottom line. In the real world, none of these things happen in a vacuum. Think about a real drive shaft. It's not a perfect cylinder, right? It's got a keyway cut into it for a gear. Well, that keyway makes it a non-circular shape, so now it's subject to warping. And what does that keyway have? It has sharp corners, which create massive stress concentrations. So on this one single part, you have torsion, warping, and stress concentration all happening at the exact same time. So I'll leave you with a final thought, or maybe a challenge. Now that you have this new lens, now that you can kind of see the invisible flow of stress, just take a look at the engineered world around you. Where are the hidden stress risers in the frame of your bicycle, the handle of your coffee mug, or the legs of the chair you're sitting on? I promise, once you learn to see them, you'll start seeing them absolutely everywhere. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.